Hello everyone, good morning to all of you. Uh, LNT College Multimedia Studio welcomes again to all of you in particular series of video lecture. Okay, so today my topic is reactivity of alkaline earth metals, right? So as in the previous lectures, we have clearly dictated that the behavior of alkaline earth metals like beryllium, magnesium, calcium, strontium, barium, radium, the electronic configuration and electronic structure of these metals have clearly dictated their characteristics, right? So in their particular respective groups, so the atomic number as previously we have given, that is actually this is 4 and this is 12 and this is 20 and this is 38, right? And this is 56 and this is your 88. Okay. From this table, right, uh, actually it can be confirmed that the density actually for beryllium, that is 1.85 gram per centimeter cube, right? But in case of radium, so it has very high density, okay? And such differences in densities, and it is because of its crystal and lattice structure in the metallic form, or you can simply say there is a different metallic lattice formed. So that is why these metals actually have different densities. So most of the metals, they actually have a structure like hexagonal close packed, right? But larger metals like suppose barium, or you can simply say radium, they form cubic close packed structure. So depending on the lattice structure, density varies, okay? And you know that density, mass, that is molar mass upon volume. So all of you know that the alkaline earth metal or metal cation, they are actually smaller compared to the group first alkali metals. So because of the small size, it has lower volume. So because density actually inversely proportional to volume, so if the volume is low, then density is clearly it will be high, right? So as compared to group first alkali metals, so group first alkali metal possess lower density compared to the group second alkaline earth metals. So it is because of the differences in the lattice structure. So now if we come across a standard reduction potential in volt at 25 degrees centigrade. So what this data indicate actually, so minus 1.85 volt in case of beryllium, while radium has minus 2.0 92 volt. So standard reaction potential means a reaction, suppose this is your 2 plus in aqueous medium plus 2 electron, right? It forms metal in solid state. So this is the reactions. 2 plus charge, so that will be neutralized by 2 electrons to form neutral in the elemental state, that is metal. So this is the actually reduction reactions where electrons are added to the cationic species. So it means M2 plus, right, M. So this is the pair in a redox process. So M2 plus undergo into elemental or metallic forms. So these values, from these values, you can see clearly that it has actually very high value in this particular group, and the least value, so that is actually in case of beryllium. So all these values are actually they are in negative parameters. So all these metals are reducing in character, right? So all these metals are reducing. So it confirms reducing behavior characteristics. Since delta G minus NF E0, right? So that is, you can say this is E0. So since all these values are negative quantity, so thermodynamically that will produce delta Z positive. It means delta G is positive, confirming that such type of reduction reactions where M in bivalent form won't able to accept 2 electrons to be converted into metallic solid. Rather, the reverse reaction is much more feasible. So what is the reverse reaction actually? So once M in solid state, okay, so is dissolved in water, then it forms M2 plus aqueous plus 2 electron. So what is actually nature of these reactions? So these reactions here, metal is in free state, so oxidation state is 0, and now here 2 plus. So such type of incremental confirms that this is actually oxidation half cell reactions. So this is your oxidation half cell reaction. Okay, and now this is your reduction half cell reactions. Okay, so reductions are not feasible because of delta Z positive characters, right? But oxidation are thermodynamically favorable. So that is why these reactions actually occurs. So formation of bivalent metallic cations are spontaneously formed. So in this case, delta G is negative. So delta G is negative, confirms such reactions are thermodynamically occur spontaneously, right? So the species which undergo oxidations, right, by releasing its outermost two valence electrons, then it turned as reducing agent, reducing agent, reducing agent, right? So which one metal is most reducing in this particular group? So from the data, you clearly see that minus 2.92, it has large positive oxidation potentials, because here E ox is equal to minus of E read, right? So oxidation potential here plus 2.92 E ox. So more negative delta Z occurs in case of radium. So radium is the most important reducing element in this particular group, right? Because of the radioactive characters, so they are not naturally used, but apart from radium, so which one has the next largest negative value? So that is actually barium. So barium has minus 2.90, which is the second largest negative value in this particular group. So it has second largest positive value. So as a oxidation potential, so you can simply say this barium is actually most reducing um, after radium, right? So barium is the most reducing, right? But the lowest negative value in this particular series is minus 1.85 for beryllium. It means it has lowest positive value. So thermodynamically, delta G is less negative uh, uh, for this beryllium. Still there is a negative value. So reaction occur thermodynamically spontaneous. So but minus 1.85 result in low reducing characters. So beryllium is the least or weakest reducing metal, right? So it is least reducing, and that is barium is the most reducing in the series. So it can be added here. Radium is the most reducing if it is available. Then barium, right? Now then strontium. Now then calcium, and then magnesium, then beryllium. So reducing character decreases in this order. Reducing character decreases. So this is least or weakest reducing metal in this particular alkaline earth metal group, and barium is the second largest reducing uh, metal in that particular group. Now we come across second ionization energy. So second ionization energy means that is IE2 in kilojoule per mole. So kilojoule per mole means the energy which is required to remove most loosely bound electrons in a isolated gaseous metal is called actually ionization energy. So since all of you know that because of the +2 oxidation state of all alkaline earth metals, so they possess two type of ionization energy. So the complete ionization energy is because of the second ionization energy. So here we have shown here second ionization energy. So that is IE2 in kilojoule per mole. So what this value actually indicate? Suppose for beryllium, so there is 1757 kilojoule per mole. But in case of uh, that is for barium, it is 965 kilojoule per mole, and again little increase in the radium, so that is actually 978. So this is because generally it should decreases from barium to radium, rather it is increasing little, approximately 13 kilojoule per mole, and this is because why this actually happens. So this is because in differences in the metallic lattice, so lattice structures are different. It may be hexagonal close packed, and it is basically exist strongly in the CCP, that is cubic close packed. So maybe there is a chances that because of the differences in metallic lattice structure, so electrons in the metals may be strongly bound to the effective nuclear charge. So it takes much more little energy compared to the barium. So that is why it has little larger second ionization energy compared to the barium, right? So this is lattice structure differences. But what you are seeing in case of beryllium, so in case of beryllium, that is 1757. So what this value indicates, that the ease of removal of electrons from the beryllium is not so easy, right? So it is very difficult, and the difficulty is due to so a small size of beryllium. So in the metallic state, so it has very small size. So all the valence shell electrons are strongly bound with the effective nuclear charge. So the removal process is actually difficult. So it takes much more energy to remove the whole, or you can say 2 electrons from the valence shell. But even it is much more compared to the first ionization energy of the group first alkali metals, right? So actually these this value are 3 or 4 times compared to the first ionization energy of the group first alkali metals. So you can say that beryllium is the metal which have more ionization energy. It means electrons are strongly bound to the nucleus, and the ionization energy is very high in case of beryllium. So it confirms beryllium is less reactive, right? So beryllium, it seems beryllium is less reactive, right? So reactive, less reactive. But what others like magnesium, calcium, strontium, and barium. In case of barium, what you are looking here, so that is 965. It means the second ionization energy for barium, so that is least in this particular series. So the barium is most reactive in this case. So most reactive, right? So the reactivity is actually inversely proportional to the ionization energy. Larger ionization energy confirms little reactivity of that particular metal. So what is the relations? Actually, reactivity is directly proportional to ionization energy, right? So larger the value of ionization energy, lower will be reactivity of the metal. So from the series, we have actually observed that barium has 965 kilojoule per mole. Means this barium is most reactive metal in alkaline earth metal, right? While beryllium, that is beryllium 17, what is actually value? So that is 1757. So 1757 kilojoule per mole, right? So it is nearly double to that value. So it is actually least reactive, right? So the reactivity varies with the value of um, ionization potentials. So third most reactive is, that is your strontium, and now calcium, and then magnesium, and then beryllium. So the reactivity order is actually order, that is your barium. Barium is most reactive, then strontium, then calcium, then magnesium, and then beryllium. So this order defines decrease in reactivity. Decrease in reactivity. So reactivity decreases. So this is the most reactive and this is the least reactive in this particular group. So because of the ionization potentials and standard reduction potentials. So in this is also confirmed from the standard reduction potential. So this metal does not undergo oxidation easily. So this is also the reasons, because it has E0 is equal to minus 1.85, right? So this is the value actually minus 1.85. In case of barium, it is minus 2.90. In case of barium, it has E0 minus 2.90 volt. So this barium can be oxidized easily, but beryllium cannot be oxidized easily. So from the standard reduction potential E0 and second ionization energy, we can explain the reactivity of these metals, right? So what is the actually configuration? As in the previous lectures, we have clearly defined all these metals, suppose beryllium, magnesium, and calcium, and strontium, and barium, right, and radium. So possess, what possess? Actually, they possess electronic configuration like NS2, right, in the valence shell. So because of the presence of two electrons in the s orbital, so this electron can be excited, right, excited in the next orbitals of same principal quantum numbers. So suppose the full electronic configuration of beryllium is actually 1s2 2s2, and here 2p is vacant, right? So that is 0. So in case of beryllium, what actually you observe in case of beryllium, so that is beryllium, in case of beryllium, so 1s2 2s2, and that is 2p0. So only here s orbital electrons are present. So in the ground state, Gs, actually we draw the orbital like 2s, and that is 2p, right? So this is your 2s and this is your 2p. So p subshell has 3p orbitals, that is px, py, and pz, and s subshell has only one s orbital. So what is the ground state distribution of these two electron? So that is actually this look like that. So both electrons are paired in the ground state, right? So here 3 orbitals are completely vacant. So actually, because of presence of these two electrons and existence of M2 plus, so these two electrons are removed, result in the bivalent charge on that particular metal. So it forms a compounds with another atom. Suppose we have X that contains two negative charge. So here M and X, if it has 2 plus charge and it has 2 minus charge. So because of the two electrons in the s orbital, so they can be easily removed to form M2 plus charge. So it can form compounds with a species having double negative charge. So because of the electrostatic interactions in these two values, in these two species, they form ionic compound, right? So all these metals actually form ionic compounds which contains M2 plus and negative species as X2 minus. So this is your MX, right? Ionic compounds. But in the practical, form. Actually, all the compounds formed through alkaline earth metals are not purely ionic. Rather, some compounds are covalent in characters. So, um, covalent characters is due to polarization effect. Suppose, and this is your beryllium 2 plus, right? And this is your barium 2 plus. So, this is actually, this species is very small, and this is large species, right? So, larger cations actually stabilize larger anions, and as per the Fajan's rules. So, the if stability of the uh, cations and anions are very high, so they are actually ionics. So, when you go or move from beryllium to radium, or suppose second reactive metal is barium. So, what actually, all these metal forms ionic compounds, but ionic character increases when we move from top to bottoms. So, because of the stability of the cations and anions, right? So, barium compounds are actually most ionics, but beryllium compounds are ionic as well as covalent natures. So, beryllium compounds possess both characters, actually ionics as well as covalent characters. So, this beryllium possess ionic as well as covalent character in compound. But barium, this metal possesses ionic compound, right? So, this is actually uh, differences in the electronegativity of the cations and anions. Suppose we have a compound that is beryllium, and that is your oxygen, right? So, in the ionic form, you know that beryllium is beryllium 2 plus and oxygen, so that is oxide 2 negative charge. So, 2 positive charge and 2 negative charge electrostatically interact to each other to form compounds like beryllium oxide, BeO. So, all the metals, actually all the metals BeO, MgO, CaO, SrO, barium oxide and radium oxide. Radium oxides are not considered here because of the radioactive characters. So, what actually happens is that once metal in the solid state, they react with oxygen which is present in the air, so they form oxide, right? So, such type of oxides are actually forms. So, beryllium oxide, right? Beryllium oxide actually beryllium, because of the small size and high charge density, so they are highly actually uh, prone to oxygens. So what actually beryllium, this is your beryllium metal. So a layer of, so this is called passivation layer. Passivation layer, that is beryllium oxide. So beryllium metal is actually passivated through a layer of beryllium oxide in the natural state. So they are not actually more reactive with the oxygens. So because of already presence of a passivated beryllium oxide layer on the surface, so without removing the beryllium oxide layer, so pure beryllium can't react with oxygen easily to form beryllium oxide, but uh, rest of the other metals like magnesium, calcium, strontium, barium and radium form actually oxide compounds. So because of the ionization of valence electrons in the metals, so this is actually MgO, right? So magnesium oxide, this actually Mg2 plus and 2 minus. So actually they form ionic compounds, and ionic compounds, you know that ionic compound forms only, so there is a differences are actually 1.8 in the electronegativity of these two metal and non-metals. So ionic compounds are actually formed through electropositive metal and electronegative non-metals. So the electronegativity of the metals actually, in case of that is your beryllium and magnesium, calcium, strontium and barium and radium, right? So electronegativity varies 1.5 to 0.9. The least electronegative element or metal is radium, and most electronegative metal is, that is beryllium 1.5, and the electronegativity of oxygen, so Xi of oxygen, that is 3.5. So what is the differences? So differences Xi 3.5 minus 1.5, so that is actually 2. So if the differences occurs very large compared to this 1.8, then the compound forms mostly ionics. So actually they are very close to the scale 1.8 and here 2.00. So this beryllium does not form purely ionic compounds with oxygen. So rather it possesses some covalency characters because of the uh, uh, match of these differences. But other metals actually they forms most ionic compounds because of the value is differences is actually very compared to this 1.8. So apart from beryllium and magnesium, so calcium, strontium and barium, these three metals form most ionic compounds. Most ionic compounds. But your beryllium and magnesium, these two metals actually forms ionic compounds with some covalent characters, and because of the electronegativity difference. So these two metals when react with oxygen to form beryllium oxide and magnesium oxide, so the electronegativity difference is not so high compared to this value. So these metals actually possess covalent characters. Covalent characters means so the bond can be formed uh, between two centers. First center is that is your actually metals, and another is non-metal. So suppose this is your X, that is non-metals. Then there will be covalent bond. So sharing of electrons between these two centers. So one electron from this and one electron from this. So there is a two electrons, which is called a pair of electrons in a single covalent bond. So some covalent character actually is obtained in case of beryllium and magnesium because they have less differences in electronegativity, and they are comparable to 1.8 or less than 1.8. So the electronegativity difference, if actually are very less compared to 1.8, it means the compounds formed through the cations and anions actually they are actually not purely ionic, rather it bears some covalent characters. So this is the actually behavior and reactivity of the all metals with oxygens. So apart from these oxides, so barium forms barium peroxides, right? Barium peroxides, so that is BaO2. This is your barium peroxides, right? Magnesium, calcium, strontium, they forms simple oxides which contains actually MO, means this metal oxide contains O2 minus as oxide anion, and barium peroxide that contain O2 2 minus. So that is peroxide anion, and this is your oxide anion. And in the previous lectures we have told that this oxide anion is smaller compared to the peroxide anion. So peroxide anion is larger anion, so it can be stabilized through larger cation. So barium 2 plus is actually larger in size in that particular group, so they can stabilize larger anion. So barium 2 plus, barium 2 plus can stabilize 2O2 2 minus. This is your peroxide and this is your barium cation. And what is the actually um, stabilization? So suppose we have a that is your barium 2 plus and peroxide exists like that, right? So O2 2 minus, right? So this 2 plus charge is actually suppose we just for the sake of simplicity we just write this barium in the center Ba2 plus. So they are actually bond like that in the lattice structure. So both oxygen can form bond with barium 2 plus to stabilize this particular peroxide anions. So barium forms peroxides, barium, that is barium peroxide, BaO2, right? And rest of the metals like your uh, calcium, strontium, and actually magnesium, calcium, strontium, they form MO, metal oxides. So what is the actually here? All metals are in their +2 oxidation state, they are -2 charge, or in case of uh, MO2 contains M2 plus and O2 2 minus. So there is no differences in overall charges. Here 2 minus 2 plus, here 2 minus 2 plus, right? So because of equivalent charges, the lattice energy is actually are not so different. They are comparable, but it is not actually comparable because of the size effect. So size of the barium 2 plus and barium 2 plus and this peroxide anions, actually it has very large interionic distance. So lattice energy will be low. Lattice energy will be low. But in case of, suppose we have a magnesium oxide, so in this case interionic distance and also the size of the oxide 2 minus is small. So because of the small size of the cation and anion, interionic distance is small. So it has very high lattice energy. Lattice energy. And the high lattice energy is because of the +2 charge and it has -2 charge. So larger the product of the charges on compounds, so electrostatically they actually interacted more strongly to form ionic compounds. So magnesium oxides, actually they are ionic compounds. Still this compound possesses some covalency, and this covalency arises because of the small and highly charged magnesium cation. So this small and highly charged magnesium cations, they can polarize this oxide anion. So Mg2 plus polarize the electronic clouds of oxide anion. So because of the polarization effect in magnesium oxide and beryllium oxide, right? So these two compound doesn't found in nature as a pure ionic compounds, rather they are found in mixed state, so that possess ionic as well as covalent characters. And the covalency is due to the polarization effect of small and highly charged beryllium 2 plus and magnesium 2 plus, and they are more prone and they are more susceptible to polarize the electronic cloud of oxide anions, right? So this is the actually chemistry behind alkaline earth metals. So oxides are formed through the reaction of the oxygen which are present in the actually atmosphere. So berylliums, actually in the previous pages we have also discussed that because of the low reactivity, beryllium does not react with the oxygen at normal temperature. So because of the surface that is unreactive, which is actually possess beryllium oxide on the surface. so they are not reactive. Now, suppose we have a MO, that is actually metal oxide. This metal oxides, either they are acidic or basic. Uh, acidic, acidic, it may be basic, or it may be amphoteric. Amphoteric. So, which metal oxides are actually acidic, and which one forms amphoteric, and which one forms basics? So, that can be discussed. Suppose that is your BeO, that is your MgO, and this is your calcium oxide, strontium oxide, and barium oxide, right? So, these three oxides, okay, when react with H2O, so that is water, in the cold state or room temperature, when they react with water, they forms CaOH का whole twice, right? Calcium hydroxide. So, because of the presence of hydroxide ion OH minus, so this compound is basic, right? Basic in character, and basicity increases when we move from calcium to strontium to barium. So, barium oxide, or you can say barium superoxide, are actually strong base. So, this is your basic compound. And barium peroxide also forms actually BaO2. So, that forms also barium hydroxide, BOH ka whole twice. So, this reaction can be balanced by putting simple the molar balance. So, because of the actually hydroxide formations, so all these compounds actually they react with water to form hydroxide. So, that is why they are called alkaline. So, they are basics. But what in case of barium oxide and magnesium oxide? So, barium oxide actually doesn't react with water at room temperature. It reacts, actually it requires very high temperature to react with water. But magnesium hydroxide so can react in a hot water. So, actually magnesium oxide can react, actually this is not the correct way. So, this magnesium oxide can react H2O hot. So, that forms magnesium hydroxide, right? So, this hot water actually is actually this reactions can occur. So, magnesium hydroxide. So, magnesium hydroxides actually possess some ionic as well as covalent characters. So, mostly in case of beryllium, so anomalous behavior is because of the small size and high charge density on the beryllium, and magnesium approaches to the reactivity also comparable with beryllium because of the size effect, right? So, all alkaline earth metals forms hydroxides, right? So, it can also forms beryllium hydroxide right? Now, what happens actually in case of beryllium? Suppose we have taken the example as that is it has 4 atomic number and general electronic configuration 2 2, right? And this is your 1s2 2s2 and this is 2p backend. So ground state, this is your in the excited state. So this 2s has also principal quantum number actually come and 2p both possess a same quantum number, that is n is equal to 2. So the electron can be excited or promoted through the uh, energized effect. And what actually happens once the energy is supplied to the system, uh, they actually one electron is promoted to 2p. So from 2s to 2p there is a transition. So one electron is promoted in this particular actually p orbital. So here one electron is in s orbital, one electron is in p orbitals. So any of the p orbital can accommodate this particular electron. So what hybridization you expect here? The mixing of s and one p orbital, they form sp hybrid compounds. Sp hybrid compounds. And sp hybrid compounds so are formed through the covalent bond formations. So sharing of suppose we have actually that is your beryllium oxide. So beryllium oxide means here two electrons are unpaired and two orbitals are completely vacant. So two unpaired electron can form two bond with that particular metals. Suppose in case of oxygen, right? So this is your 8. So 2 and 6. So what is the electronic configuration? 1s2, 2s2 and 2p4. Now this is the 2s and 2p are the valence shell. So what is the ground state configuration? Gs, that is your 2s and this is your 2p, right? So 2p actually these two electrons and here 4 electrons actually in the same spins and fourth one is in pair form. So here s orbitals and one of the p orbital is in actually in paired state. So they are not actually reactive, but these two orbital contains actually uh, single electrons in the orbital. So they can form bond with two other orbitals which have same energy symmetry and equivalent energy to form a covalent compounds. So here in case of beryllium oxide, what happens? They form actually combined sp3 hybrid orbitals. In the oxygen in the excited state, actually in the ground state, not excited state, in the ground state, they form sp3 hybrid orbitals. Two unpaired electrons so can form a bond. So right. So two unpaired electron, two sp3 hybrid orbitals can mix with the two sp uh, hybrid orbitals. So two sp hybrid orbitals and two sp3 hybrid orbitals can mix to form uh, two covalent bonds, right. So in this case, actually, beryllium possess such type of structures, two bonds, right. One single bond and another maybe a pi bond. So depending on the which type of actually orbitals taking parts. So this sp and this sp3 is due to single bond, and this sp and this sp3 may be due to the uh, sideways overlapping, so they can form pi bonds. So because of the presence of two double bonds and extent of 2 plus charge and 2 minus charge, so beryllium oxides are actually not purely ionic, rather it is covalent in character. So similarly, magnesium oxides possess some covalent characters, right. Now in case of beryllium oxide, what happens, you look here, this is your in the excited state, one electron, this is your one electron, 2s and 2p excited state of beryllium, right. So once they form a covalent bond, so here pairing occur, and still these two orbitals remain vacant, remain vacant. So the octet rule is not complete in case of beryllium. Around the beryllium, only 4 electrons in the valence shell. So beryllium oxide, this beryllium uh, possesses only 4 electrons in the valence shell. So compared to octet rule, so there is deficiency in the octet configuration. So that is 4 electrons, and that 4 electrons, if beryllium is susceptible to form actually compounds, are able to accept the electrons from bases or the species which are able to donating the its electron. So beryllium oxide are electron deficient, electron deficient compound, right, electron deficient compound. And this electron deficiency arises due to presence of vacant two orbitals. So they can actually accept pair of electrons from the bases or ligands. So they are also Lewis acid. So Lewis acid actually accept a pair of electrons. So beryllium compounds or beryllium oxides, actually they are Lewis acids. So in the group beryllium oxide and beryllium oxide, this is your compounds, and they are amphoteric actually, and it has both acidic character and basic characters. So acidic characters actually because of the um, reactivity with H2O, and acidic character is because of the reaction with acids in the water. So this compound actually is amphoteric in character. Amphoteric in character. So actually we have some reactions, so that clearly gives us idea about the acidity and basicity or amphoteric characteristics. So that is actually in case of reactivity, actually what we have actually some reactions. The reactions like actually then this is your reactions here, right? Once beryllium oxide react with H2O, so BeOH का whole twice it forms beryllium hydroxides. So it further react with suppose in the next page, beryllium oxide react with H2O, beryllium hydroxide, right? So now this beryllium hydroxide is unsaturated, and they further react with hydroxide anion in a 2 molar, they forms BeOH का whole thrice, that is your 2 minus. This is your complex ion. So this beryllium oxide is acidic, Lewis acid, right? Lewis acid, and that can react with the Lewis base. So this is your hydroxide ion, that is your Lewis base, right? But same compounds actually react with your acids also. So suppose we have barium hydroxide, beryllium hydroxide react with 2 mole of HCl, and in the water, so what product forms actually, that is your BeOH का whole 4, and so this 2 minus actually that is your Cl2, right? So this is your BeOH का whole 4, this is your 2 plus, right? So 4 minus actually, and so similarly, so this is your compound here, B2 plus and 2Cl minus, that will be stabilized. So this is called berylate ion. This is your berylate ion, BeOH का whole 4 2 minus. The same beryllium hydroxide react with acidic medium, and beryllium hydroxide reacts with basic medium. So 4 hydroxide actually forms a bond around this beryllium. So this is actually in this case they are Lewis base. So acidic behavior from these reactions and basic behavior from these reactions confirms that uh, the compounds are actually amphoteric. Amphoteric, right? So most of the actually beryllium and magnesium oxide compounds are amphoteric in characters. So because of the reactivity of with bases as well as acids. So in the next hydride formations. Hydride formations. So hydride formations means uh, hydride ion, that is H minus. This H minus is diamagnetic in characters. As you know that uh, this species contains 2 electrons. So this is your diamagnetic. Now because of the presence of negative charge, this act as a strong base. So strong base, or you can say Lewis base. So Lewis base, and this is also reducing, right? Reducing in character. So all the alkaline earth metals, that is your beryllium, magnesium, and calcium, strontium, and barium, right? So they react with actually hydrogen gas, forms a compounds like that is CaH2, strontium H2, and barium H2, calcium hydride, strontium hydride, and barium hydride. Beryllium does not react directly with hydrogen because of the passivation layer on the surface of the beryllium. So without removing the oxide passivations, it cannot react with hydrogens. So actually they are prepared from the actually halide compounds. So magnesium magnesium forms that is actually uh, MgH2, right? So here Mg 2 plus and 2H minus exist in the ionic state. So Z plus Z minus that equal to 2. So the lattice energy of the compounds are actually due to presence of 2 positive charge and 1 negative charge. So 2 times compared to the first group alkali metals hydrides like lithium hydride, sodium hydride, and potassium hydrides. So the lattice energy is very high, 2 times compared to the first group alkali metal hydrides. So they are most stable. But what happens actually, these hydrides upon heating, suppose we have calcium hydride CaH2, once it is heated, to 250 degrees centigrade. So they release calcium solid plus hydrogen gas. The hydrogen gas is produced upon heating the metal hydrides. So this type of compounds actually act as a hydrogen storage. So all the alkaline earth metal hydrides acts as hydrogen storage, right? And what happens when specific hydrides, that is calcium hydrides or any other hydrides, react with actually 2H2O, right? So they also produced that is calcium hydroxide, OH2, and this is your H2 gas, right? So H2, this is your gas. So calcium hydride react with water at ambient temperature. So this forms calcium hydroxide, so and hydrogen gas. And these reactions also produced hydrogen gas. So you can say that alkaline earth metal hydrides are a very important source of storage of hydrogen energy nowadays in the research and innovation technologies, right? So this is the actually beauty of compounds like hydrides in alkaline earth metals. Okay, so rest of the reactivity like reaction with nitrogen, reaction with actually halogens, or you can say any other complex anions, so can be discussed in the next video lectures. So hopefully I understand that. So this video lectures are I think it will be more comfortable, beneficial, and energizing, inspiring to your brain. I think please don't forget to like, share, and comments on this particular video. So thank you, students, for listening and watching the video lectures focused on alkaline earth metal and its reactivity. Thank you.